The book uses this binary compounds categorization of type 1, type 2, and type 3. Sorry about that. It is kind of tedious, and if you know what things are anyway, you don't really need to memorize this. It's sort of their flow chart for helping you. Okay, so one thing we kind of just touched on yesterday was sort of the way that people write molecular formulas. You can just think about like Burger King. So at Burger King, if I wanted to like come up with a name for this burger that has 2 buns, 2 patties, 2 layers of cheese, and bacon, I would go, well, that's bun. There's 2 of them, so I put a subscript of 2 there. Bacon, there's 1 of them, so I don't put a subscript. It's an implied 1 bacon layer. And then there's 2 meats, and there's 2 cheeses. The 2 describes what's to the left of it. The subscript describes what's to the left of it. To do it again, another example, right? There's only 1 bacon layer, so there's just write bacon, 2 buns, 2 meat. There's 3 of them. Cheese, 3 of them. I'm not endorsing Burger King. Please, in moderation, don't kill yourselves based on this lecture. We can do this one as well. So this burger has like 2 buns, 2 burgers, 2 layers of cheese. Don't look at that sauce. Forget that's there. This is from Jack in the Box, in case you're interested. And I could write bun 2, meat 2, cheese 2. And again, I'm ignoring the sauce, right? So I could say that it has 2 buns, 2 meat, and 2 cheese. So that's the molecular formula. If this was like a molecule, that would be how I would write the molecule. If this was an ionic compound, I would write the empirical formula. I would actually divide the subscripts by common factors. So because there's 2 buns, 2 meat, and 2 cheese, I could just say, well, that's a ratio of 1 bun to 1 meat to 1 cheese. So sometimes you'll see both. Like you'll see a salt that people will reduce beyond its molecular formula to a empirical formula. All right, we can also think about, based on the molecular formula, how many of each element are in that molecule or in that empirical formula. So sodium sulfide has 2 sodiums and 1 sulfide. Does that make sense to everybody? Right? Because the 2 describes the sodium. There's an implied 1 here. It's not there. If there's nothing, it's 1. 1s. So there's 1s, 2 sodiums. Here, same thing. Here's another example, but it gets more interesting. The 2 is describing everything in those parentheses, so both the O and the H. There's actually 2 OHs, which means there's 2 O's and there's 2 H's. You can do more than 2. Like this is a molecule as opposed to ions and salts. Straightforward stuff, I hope. Again, if you don't see that number, it means a 1. It gets a little bit more interesting when there are subscripts inside the parentheses. So like here's calcium phosphate. There are 3 calciums, right? Because that 3 describes the calcium. That 2 describes the phosphate, the PO4s that are in there. There are 2 PO4s. So that means that because there's only 1 P per phosphate, there's only going to be 2 phosphorus. And because there's 4 O's in each phosphate, there are 2 of them, so that means there's going to be 8 of them total in the molecule. We went over periodic table of the elements. We looked at how to figure out what charge. Sure. Yeah. Any questions on the stuff, or are you guys just sort of writing out? Okay. I will provide these online shortly, like tomorrow morning at the latest. These are pretty well done with the Roman numeral missing here and there. Are you guys ready? No. Okay. So last time we talked about position in the periodic table and how that relates to. You guys ready or? Okay. And if you want to copy it down during the break or something, that's cool too. But it will be up online, I promise, very soon. We were talking about how you could determine what the charge of an element in an ion would be based on its position in the periodic table. And we said that this first row would give you +1 ions. So in a salt, in an ionic molecule, sodium, Na, would be Na plus 1 because it's in this 1 column. Elements in this column would give you plus 2 ions. Transition metals are trickier. I think on ALEC sometimes you do see scandium, give that a plus 3, give yttrium a plus 3, but generally they get really tricky, especially as you move this way. And aluminum is plus 3, gallium is plus 3, indium is plus 3. But then after that, you can't really say too much about carbon or silicon. And then when it gets closer to the noble gases, they start to behave as anions. These are called nonmetals. And the stuff we were talking about before, this whole area here, including the transition metal area right here, these are called metals. So metals tend to give positive ions or cations, and nonmetals tend to give negative ions or anions when they're in ionic compounds. Fluoride, chloride, bromide, iodide, these things have -1 charges. Oxide, sulfide, selenide, these have -2 charges. -3 over here. You guys get the drift. There's ambiguity here, so we're going to learn about how to name things and think about things today given that ambiguity. There's ambiguity about the charge of lead and tin and thallium. We'll talk about that. Yes? Just what I said before, like here, a little bit written out for you. -1, -2, +1, +2, +3. Transition metals are, again, we need more information to deal with them. And even with tin and lead, we need more information to deal with them because we don't know what's going on without more information. So the book decides to make this into a big deal. When you have those elements that behave, you know exactly what the oxidation state is. It's always going to be a +1. It's always going to be a +2, depending on what it is, where it is in the periodic table. It calls those type 1. If there's any ambiguity about the charge, if sometimes the element's +2, sometimes it's +3, that's type 2. And then if there are 2 nonmetals bonded together, they call that type 3. I don't require that you know which is what kind of type. If that helps you name things or think about it, great. But I'll probably just slide into saying like ambiguous versus not ambiguous and 2 nonmetals. Here's how you name ionic compounds. The simple rule of thumb is that the positive ion, the cation, the thing that lost electrons, is going to be named first, and then the thing that's going to be named second at the end of the name is going to be the anion, the negative ion, the ion that gained electrons. And we changed the negative ion to have "ide" at the end. So instead of sulfur, it would be sulfide, or instead of oxygen, it's oxide. Sodium chloride is sodium chloride. Here's a table that just shows you how to change the names. It's not that exciting. Get good at this. I still make a mistake with this. For some reason, I always put a pH there, and I have no idea why. And it's really, really annoying. So I would not get 100% in this class. So for type 1, we have a metal cation that we know the charge, and we have a nonmetal that we know the charge. So lithium, it's in that first column, so it's going to be +1. Fluoride is in that column right next to the noble gases, so it's -1. So we know exactly what's going on here. It's pretty easy. Lithium fluoride. If I tell you lithium fluoride, you know that it's this. There's no ambiguity here. Lithium is not going to be lithium +2. It's not going to be lithium +3. It's lithium 1, and fluoride is a -1 charge. Okay, everybody, what do you think? What's the best name for KCl? Yeah, okay, I think we have a majority. So yeah, B is correct. Potassium chloride is the best name for KCl. So potassium is the metal. It's the thing that's in that first column in the periodic table. So it's potassium 1 +1. And then the chloride is the negative thing. It's the anion. So it's going to be not called chlorine, but called chloride.